Well, hello everybody. My name is Ciaran. Hopefully I'm going to give a talk at least a quarter as interesting as the last one, which I really enjoyed. So today I'm going to talk about counterfactual interesting, why it's interesting, what it's good for, how we should do it. And along the way, I'm going to really try and ground the discussion by giving lots of practical examples, real world cases where we need to use this type of reasoning and so forth. Okay, so along that line, let's start with a fun example. So here is a prominent anti-vaxxer taking to Twitter in 2021. And he's showing some data taken from the Office of National Statistics in the UK. And what he's plotting is the death rates among people who've been vaccinated versus people who haven't been vaccinated to COVID-19. And you can see a strange pattern start to emerge. The orange line here is the death rate after people have received their second vaccination, and the blue line is no vaccination. So a strange thing is happening. There's an increase in the death rates among those who've been vaccinated. This seems strange, right? COVID-19 vaccine should protect us from mortality rates from COVID, but the data is saying something completely different. So what's going on here? So he was kind of using this as a way to kind of suggest that perhaps it's not the best policy that governments vaccinate their populations and so forth. So looking at this data, it seems like a reasonable thing to do. But if we dive a little bit deeper into the data to kind of figure out what's going on, there's a big confounder here, and that's kind of skewing the observed correlations we're seeing and kind of obscuring the underlying causal relationships. So what's actually going on is the average unvaccinated person is much younger than the average vaccinated person, because older people, they were allowed to get their vaccine earlier and so forth, and they think it's probably more important because perhaps they're more at risk of COVID, so they're more likely to get the vaccine in the first place. So therefore, people who've been unvaccinated have a lower mortality rate just because they're younger, right? They're less likely to die from other causes than COVID and so forth. So any benefit from the vaccines is swamped by the increase in mortality as we age. So age here is a confounder. It's influencing both whether you get vaccinated and also what the impact of that vaccination is on your mortality, for instance. So the question we have to ask now is, what's the actual causal effect of being vaccinated on your mortality rate? Because we've done all of these randomized control trials that have showed that vaccines reduce mortality and so forth. So clearly there's a proper causal relationship here that vaccines are good for us, but the data is kind of telling us something different. But when you control for age, you hold age fixed so that in both vaccinated and unvaccinated cohorts there's an equal distribution over age, then indeed the correlation goes back to what we would expect given what we've seen in our randomized control trials. So after this came out, the Office of National Statistics had to put a big disclaimer on their website where you can go and look at the mortality rates from COVID and so forth, highlighting this kind of bias that's being brought in by age and suggesting people should reason about it, in some appropriate fashion. So the kind of take home from this is that any action or policy change based on these correlations, such as whether we should vaccinate a population, would not have increased patient survival. So relying on correlations extracted from observational data can lead to embarrassing, costly, or in this case, dangerous mistakes. So to overcome this, what we need to do is reason about cause and effect rather than just looking at raw correlation. Cool. So how do we do this? Well, the gold standard is usually running in what in industry is called an A/B test, but in the kind of medical literature, we call these a randomized control trial. So when we do this, we kind of randomize whether you receive treatment or not, so any kind of influence of a confounding variable is removed because it is random allocation. And so we can truly reason about cause and effect in these situations. But there's lots of cases where we can't run A/B tests or randomized control trials. For instance, they could be too damaging to the user experience. They could be technically too hard to implement. So if I want to figure out if app bugs or crashes on your app cause users to leave that app service, then I can't really do a randomized control trial where I force some users' apps to crash because that just might annoy them a lot. Or I want to figure out in the context of Spotify, does podcast consumption really cause users to stay around more, or is it some combination of other things? Again, to do a randomized control trial here, I'd have to remove all podcast content from Spotify, which probably would have knock-on consequences and probably is a difficult thing to convince people that is the right thing to do. And on the kind of more physics side of things, if I want to figure out if the moon is causing the tides on Earth to change or vice versa, I can't really go out and move the moon around. Well, in principle, I could stick some rockets on it, but it's not technologically feasible to do these things. So lots of times we can't do this kind of perfect gold standard way to figure out cause and effect relationships. So that's where causal inference comes in. And so, it's a field that has a bunch of tools that, allows us to quantify cause and effect given certain assumptions. And even when we can't do these A/B tests, so it's super powerful. And so what I'm going to talk about today is what a causal model is, what we can do with it, but a focus on a very specific type of inference we can do with causal models. So first, let's kind of define what a causal model is so we're all on the same page. And then I'll talk about the different types of inference we can do when we have access to such models. So the kind of basic idea is we have some observed terms. So here, in this case, the observed terms are the kind of orange or yellow nodes. And we also have some sort of noise terms telling us, factors that are influencing these observed things that are outside of our model. So they're the green things in this kind of thing here. And the general assumption is that noise terms are kind of distributed according to some unknown latent distribution. And the observed terms are a deterministic function of the parents of that node in the graph together with these unobserved noise terms. So you might say, okay, well, this is strange. Why is there this underlying determinism in my graph? Surely these kind of causal graphical models, sometimes people refer to them as Bayesian networks, they assign joint distributions across these observed nodes, but you're telling me there's deterministic functions underlying this. This is kind of strange. But the point is that we don't know what the distribution of the latent noise terms is, so that uncertainty then propagates through these deterministic function to give us uncertainty about the observed nodes and so forth. So together, all this information jointly generates, joint and conditional distributions over the observed nodes. So we have all this structure. We have this joint distributions and the functions underlying them. And the question is, when we have this, what can we do with it? So Pearl, who's one of the kind of fathers of causal inference in the computer science community, kind of defined what he called a causal hierarchy. So 3 things that we can do with a causal model. So at the first layer, what we can do is talk about standard Bayesian style inference, asking what the joint probability of certain outcomes might be, the conditional probabilities and so forth. Then the next level is what he calls interventions. So these are things that talk about how to kind of simulate an A/B test using, let's say, just observational data. And then at the very top of the hierarchy, what Pearl defined as are counterfactual, so ways that he said are something akin to imagination. So I'm going to talk a little bit more about these in detail to give you some examples. So the kind of standard example in causal inference is the question, does smoking cause lung cancer? So in lots of cases, there might be unobserved factors, like in our vaccine example, that could predispose people to smoking, but also to getting cancer in the first place. So it could be some underlying genetic precondition and so forth, or various other kind of factors. And at the first level, what we can do is ask, okay, given that I've observed somebody smokes, what's the probability that they have cancer? So they're the types of questions I can talk here. The next level, interventions, is kind of simulating randomized control trials that we talked about a few slides ago. And this is a kind of crucial bit of Pearl's kind of formalism, in that he introduces this thing called a do operator. So it's meant to kind of formalize this idea of reaching into my model and forcing some variable to take a certain value. So this is kind of what happens in a randomized control trial. I'm forcing some randomly selected group of people to smoke, forcing another subset to not smoke. And this do operator, this kind of do notation here, is what's telling me that. So the difference between this and the previous kind of notion of just doing observational inference is that I've observed someone smoking in the previous one, and that could be due to other factors such as genetic predispositions and so forth. But in this case, I'm observing the fact that I intervened and forced them to smoke, so I'm acting in the world. And this is kind of how I should think about what randomized control trials are. And then at the last level are these counterfactual things. So they really are kind of truly what-if types of questions. And it's slightly different to the interventions on the previous slide. And it's kind of slightly, it sounds quite complicated. If we look at this distribution here, we see cancer, this C variable, appear on both sides of the conditioning symbol, so it seems very strange. But actually, when you unpack this, it's quite intuitive. So what I've done is I'm saying, okay, I've observed that the person has cancer. And I want to say, in that context, if I had forced them to not smoke, I want to then ask, what's the distribution over them not having cancer? So cancer being false in this kind of situation here. And this seems like a kind of quite a complicated expression to try and estimate what's going on. Cancer appears on both sides. How do I do this? So Pearl introduced a nice 3-step inference procedure to kind of figure out how we should estimate these types of counterfactuals. So the first step is what he called abduction. So it's saying, okay, I've observed some evidence in the real world. So in this case, I'm looking at, given I've observed someone smokes and they have cancer, I've observed that in the real world. So now I'm updating my knowledge about any latent distribution. So, the likelihood that they have a gene that might predispose them to smoking and kind of so forth. So I'm updating my knowledge about that. In that context, I then apply this do operator, I reach into my model and I force the subject to not smoke. And then what I want to do is, in this new model where I've done this intervention, this graft surgery, I take this new distribution, this updated distribution over my latent, and then I kind of feed forward. So I sample from that, and I kind of feed forward and predict what the distribution over having cancer or not is in this kind of updated model. And so this kind of procedure tells us how we can estimate those strange counterfactual looking things at the top. So to kind of give a quick illustrative example of what's going on here, here's a kind of nice case from kind of medicine. So what I've got here is this 3-layer network. The top, I have a risk factor about someone being overweight. The next layer, I have possible diseases that risk factor causes. And then at the last level, I have kind of symptoms. So symptoms that are caused by the diseases that are linked to the kind of risk factor and so forth. So what I want to ask here is, given I've observed a patient has these symptoms, they're present in the person at a given time, I want to now say, what would have happened to them? How likely would it be that they're still there had I intervened and cured a specific disease, or reached in and turned off a disease, for lack of a better term. So the diseases here, I'm assuming, are just binary variables that tell me if that disease is present or not. Okay, so let's use Pearl's 3-step procedure to do this. So the first step is I've observed this evidence, and now I want to abduct, so update the kind of model, the parameters of my model given that I've observed that. And then I want to do this action. So I want to reach into my model and cure a specific disease. So I kind of sever any incoming reasons why a specific disease, in this case angina, might be there, turn it off. And then in this context, I want to feed forward and kind of figure out what's going on. So I kind of predict and pull everything down to what's going on. So that's the kind of process of how one can compute these counterfactuals. So I've said that we have this nice 3-layer hierarchy. And at the middle layer, I've said these interventions simulate randomized control trials. And I said at the start that randomized control trials are these kind of gold standard for doing causal inference. They're what we should try and figure out. But I've never said anything about counterfactuals being useful. And actually, when I was reading the kind of literature on this, I couldn't find any key examples, real-world cases where counterfactual reasoning was super important for the outcome, and I couldn't have done the same type of reasoning by just talking about interventions and so forth. So what I want to talk about today is there any context in which counterfactuals can offer some form of advantage in reasoning over observations or interventions? And so the way I'm going to do this is I'm going to explore that example I just gave about medical diagnosis and kind of see, do counterfactual reasoning play a role in kind of how we should formalize this from a kind of machine perspective. Okay, so before I kind of dive into that, I'm going to talk a bit about the disease model that we're going to use and do counterfactual reasoning on top of. So here we have this 3-layer kind of network, risk factors, diseases, symptoms, and so forth. In the kind of context of the next few slides, we're going to assume that we have this structure given to us. So some medical professionals or epidemiologists and so forth might have gone into the literature, taken their domain knowledge and said, okay, I know this risk factor causes this disease, but not this other disease. I know this disease causes this symptom, but not this other symptom. So they input this kind of graphical structure there. We then go and kind of look at the population and say, how likely are these risk factors among the population? How likely are these diseases? And kind of so forth. So we have both the graphical structure, the orientation of the arrows, as well as kind of joint distributions and conditional distributions over this. So we're taking that as a given. And the question is, if I want to kind of diagnose a patient, how should I do it? So what's going to happen is I have this big model that's been given to me by experts. A patient comes in, we kind of take from them what symptoms are present. Did they have a cough? Did they have a headache? Various sort of things like this. I then input these into my model, and what I want to do is infer the disease that's causing these symptoms. So this problem goes back to the kind of mid-'80s where people were trying to make this an automated process. Given a model, how do I figure out what disease is kind of underlying or could explain the symptoms? And the standard way that they do it is just using posterior inference. So they say, given that a certain set of symptoms are present, and moreover, I know this specific patient has these risk factors, what's the probability that a certain disease is true in this case or is likely? And then I can just say, okay, looking at all the diseases in my model, which one is most likely given all this evidence? So that's the kind of standard way of doing it. The way I'm going to propose today is instead formulated in terms of counterfactual inference. So what I'm going to say is, given that I've observed a certain set of symptoms are there and some risk factors, and now if I reached into my model and set a disease to be off, so I cure a hypothetical disease, I want to ask, in that new context, is it likely that the symptoms are cured? And if not, then I'm going to say, okay, this disease is not causing your symptoms, But if that has a high probability, I'm going to say, okay, this disease is a good candidate for causing these symptoms, and it explains them really well. So why might we expect the counterfactual approach to work better than the standard kind of posterior ranking approach? Well, if I go back to this graph I had a little while ago, and I look at what happens here, so I observe certain symptoms, shortness of breath, chest pain, and so forth. I then I do a standard Bayesian update my model. In this case, what we can see is if those things are there, then it's highly likely that the patient belongs to a population that was overweight. And moreover, if they belong to such a population with some high likelihood, they have diabetes. Again, this is a hypothetical example. And in this case, diabetes does not cause the symptoms, right? It has no causal link here. But yet, it's very likely, given the evidence, right, that this person belongs to this subpopulation and so forth. But in this case, diabetes would be a bad explanation of my symptoms because there's no causal link. If I reached in and somehow cured the patient's diabetes, maybe giving them insulin and so forth, it would have no effect on their symptoms. So a doctor would never do something like this, right? Because they want to find a thing that if they reached in and provided treatment, they could reduce a patient's symptoms and so forth. Whereas in this case, that wouldn't happen. But the counterfactual case would account for this, right? Because if I updated my knowledge, I see diabetes is quite likely, but now I reach in and I cure diabetes, it's going to have no effect on the symptoms. So it would be a bad explanation in this case. But something like angina, for instance, has this kind of strong causal link, and so it would have a high probability in the counterfactual sense, and so would be proposed as a good kind of explanation of my symptoms. So that's kind of why we might expect it to work. How do we actually go and test this in the real world? So what we did was we got a kind of panel of doctors, and they compiled about 1,700 medical cases, and these are kind of very similar to what kind of trainee general practitioner doctors are given before they become qualified. They have to go in and kind of they're given a case like this, given some evidence, background on the patient, and they're kind of told, okay, this is the actual disease that this panel of doctors thinks is really likely in this case, and a good doctor would infer this from all the information. That disease is then hidden from the doctors and from our kind of algorithm, and we want to infer from all of this information what the most likely disease is. And then we can kind of score the approach by saying, okay, is this disease that the panel of experts thought was the kind of right disease in this case, is that inferred by the algorithm? And so what we want to do is output a ranked list of diseases. So all of the diseases in our model, let's rank them, how likely they are given all of this evidence, and then we want to compare whether the disease actually on the card is in the top K of this ranked list for all the kind of output ranking of our diseases. And we're going to compare the counterfactual approach to the kind of standard Bayesian updating approach. So the important thing to note is that the underlying disease model here stays fixed, so nothing changes. All that changes is that we're changing the way we do inference on top of this model. Cool. Okay. So you can kind of see here the slight difference as we're kind of increasing K. So we're looking at, okay, the list of diseases, the top disease, top two diseases, and so forth. The causal model using this counterfactual reasoning is getting to the right answer kind of quicker. In a sense, it's always higher up the ranking than it would be for the standard kind of machine learning approach where we're just doing standard Bayesian inference and so forth, which is definitely very nice. The real question then is, if we compare to real doctors and compare their kind of inference capability on the same set of tests, how does the standard Bayesian updating approach compare to the counterfactual approach? So we took 44 doctors who weren't involved in creating these 1,700 kind of cases, and we compared how both algorithms did to how the doctors did. And you can kind of see here on the top, we have this kind of red line. If you're above that red line, the algorithm is doing better. If you're below that red line, the doctors are doing better. The same for the counterfactual here. And you can see that in the counterfactual case, the algorithm is doing much better than the kind of doctors in general. So it's places in the top 25% of doctors, where the standard Bayesian updating approach places in the top 50% of doctors. So still pretty good, but we get this extra boost from reasoning counterfactually, which is pretty cool. And a kind of important thing to kind of note here is that when you look at the kind of bottom left quadrant here, this is a case where doctors found the kind of cases really, really difficult, right? Their accuracy on certain cases was very hard, but in those cases, the algorithm always performed better. So it always kind of was able to outperform the doctor there. But when we went up and found cases that the doctors found were easy, perhaps they see them a lot in their clinical practice and so forth, they were outperforming the algorithm. So that's something kind of interesting to kind of focus on. Perhaps there could be some nice symbiosis between doctors and AI, where for really challenging cases, the kind of algorithm could suggest certain things the doctor could think more about. But in cases where the doctor has seen it a lot, they can just go with their gut, and that's kind of the right thing to do. So that's kind of great. If you're interested in kind of reading more about that, it's up on the kind of archive there and so forth. We got some nice press about this when it came out, which is always good. And so what I kind of asked at the start was whether counterfactual inference is useful for something. So what we've shown there is, at least in the context of medical diagnosis, it was useful, which is fantastic, right? We answered that question. But then the next step is saying, OK, can we generalize this to other types of problems where we might want to reason counterfactually? And the thing I should kind of point out here is that we got this advantage, but in a not very generalizable way. The model that we had constructed, the structure was given to us by experts, but moreover, we kind of imposed a parametric model relating how risk factors cause diseases, how diseases cause symptoms, and so forth. So we can't really generalize this to just saying, give me some raw data, I'm going to train a causal model on it, and then do counterfactual reasoning. We kind of used what's called a noisy OR model in this case, and the reason for that is it's well used in the medical literature. It also kind of tells us that if we have multiple diseases causing the same symptom, if I observe the patient has another disease, it can only make the symptom more likely. It can't reduce the likelihood of the symptom, which makes kind of intuitive sense in the domain of medicine. So the question is, can we answer counterfactual questions from data without the need for these parametric assumptions? Can we do it using sort of fancy neural technologies and so forth, so that we can now kind of scale and apply this in many other domains where we might not know what the underlying functions should kind of look like, where we just have raw data and so forth. The other question is, do we need to, right? Are there cases where it actually would be useful to do this counterfactual reasoning? And then the last question is this even possible? Do we run into any kind of extra problems when we try and do this without the use of a kind of parametric model? OK, so here is our second motivating example, which is kind of hopefully designed to show that it's useful to reason counterfactually in other contexts. And so here, there was an NGO that kind of went into Africa, and they kind of saw that diarrheal diseases were a leading cause of disease and mortality in the developing world, especially among young children. So to reduce the kind of likelihood of young children getting these diseases in a certain area of Western Kenya, what they did was they went in and they kind of built wells like the one on the kind of top right-hand side here, where you looked at where the kind of local kind of people were going to get drinking water. You set it up so that there wouldn't be kind of mud and bacteria in the water when they're collecting it. And they wanted to see, would this reduce diarrhea? So what they did was they set up a randomized control trial where they selected villages at random, went in, built these kind of wells and so forth, and compared the incidence of these diarrheal diseases in between these kind of two contexts. So they found that spring protection significantly reduced the diarrhea for children under age 3 by about 25%. So that's great. I mean, that seems like a really kind of useful thing to do, help people in the developing world and so forth. So the next question is, should we scale this intervention up? Is it the right thing to do to now go across Africa and reproduce this kind of intervention in all kind of cases where we find such kind of water sources and so forth? So it's really expensive to kind of do this. And so most NGOs, they want to make sure that they're allocating resources in some optimal kind of fashion. So they want to figure out, is this the right thing to do? Did we actually see an effect of the spring protection, or was it something else about us perhaps going into a village, educating the people by saying, OK, we're building this well, it's meant to reduce diarrhea, and the reason it does that is it stops kind of bacteria getting into the water. Was it just that educational element, or was it the actual intrinsic thing of protecting the spring itself? So the question that we really need to answer in this case is, how likely is it that the negative outcome was caused by exposure to diarrhea, in the kind of bacteria and so forth, and not something else? So the question that we kind of want to answer is, given a child developed diarrhea after drinking from an unprotected spring, would they have still developed diarrhea had they drank from a protected spring? So it's a counterfactual question. It's precisely one of the ones very similar in structure to what we asked about kind of diagnosis. So it's another case where answering counterfactual questions would be super important for deciding whether to kind of go in, scale its intervention up, and provide the right benefit, or whether there's something else we should look at that could be perhaps cheaper to scale up and kind of provide the same level of benefit. OK, so let's introduce a little bit of notation just so it's easier to kind of talk about these questions. So what I'm going to say is capital Y with this subscript x equal to little case x is the value of y when we intervene with this do operator. So that's the kind of notation I'm going to use for describing this thing. And now we can introduce some sort of new causal questions, which are, for instance, what's reproduced here, which is the probability of necessity. So given I've observed that x is true, so I'm dealing with binary variables x and y. So I want to say, given that I've observed x is 1 and y is 1, and perhaps there's some observed confounding going on here, some sort of context and so forth, so a condition on that as well. I want to ask, in this context, what's the probability that y would be 0 had I intervened and set x to 0? And so this is the probability of necessity, and it really tells us that what the probability of event y would not have occurred without event x occurring, given that x and y did, in fact, occur. So the question that I really want to answer here in the context of this spring kind of case is the following. So given that a person developed diarrhea from drinking from an unprotected spring, what would the likelihood of them still having or not having diarrhea had I protected the spring? So I want to figure out the answer to this specific question here. So here's where we hit our first speed bump. Is it possible to even learn such a thing from data? And so the question we want to ask is if this quantity is identifiable from the type of data we have access to. So given observational data and data from the interventions that have been performed, can we infer what the answer to this counterfactual question is? And what we want to show is that a kind of quantity is identifiable from a specific type of data if every model that agrees on that data produces the same value for that quantity. So I want to see that if I can show there are two models that exist that agree on the data I have access to, so the observational data collected from the springs, the interventions that I performed in a randomized control trial, would those two models agree on the counterfactual question I want to ask? Turns out for counterfactuals, the answer is no, you can't always do this. There are certain counterfactuals, even when there isn't unobserved confounders, where you cannot identify them from observational or interventional data. So here's a kind of quick little example. If A and B are just, again, binary variables, the standard basic kind of causal model here is kind of described as follows. So without loss of generality, A to B is the mapping between two bits. So it's a kind of four-valued function here. So the mapping can either be the identity, a bit flip on A, it can be throw A away and prepare 0, it can be throw A away and prepare 1. And what's going on here is the noise term up there on B tells me which one of these cases it is. So kind of sample from that, conditional on that, it tells me which one of these functions it is. This is the most general type of kind of causal model between two bits. And you can kind of see that this model is completely specified by the distribution over my latent variable up here. So if I know what that distribution is, I can tell exactly what the causal model is. And looking at this, U is a four-valued variable. So a distribution over it has three real parameters. It's normalized, so that kind of cuts out one. So what we want to ask is just from kind of observational data, so conditional distributions between A and B, does that perfectly constrain my causal model? So on the previous thing, I saw that this model had three parameters, but the conditional distributions only have two parameters. So there's one free parameter left that I can use, in a sense, to construct two different models that agree on those conditional distributions, but disagree on that last parameter and hence have different counterfactuals. So here's like a specific example, kind of relating these quantities to the parameters of my model, and I can kind of see that for certain counterfactual questions, the way it's related to a parameter, I cannot infer that parameter from just conditional distributions. So there's no way for me to learn this counterfactual distribution from data. So I need to do something else. I need to kind of impose extra constraints in order to learn this kind of quantity. So what we need to do here is add these extra constraints to infer what these counterfactuals are. And so the question we might ask is this actually a problem? Like, will this run into any issues if we're trying to reason about counterfactuals? Or can we just trust any model that reproduces the observations that I've seen? So to kind of give a quick overview of this, we took some data from the German credit data set. So we have an individual's account status and other financial data, as well as whether they were approved for a loan, how risky they might be, and so forth. And from this data, just kind of looking into it, we see, as we would intuitively expect, all else being equal, the better the account status and how much money is in there, the lower the loan risk. So the more likely that the person will be given a loan. So it seems intuitive. If you increase your account status, your likelihood of getting a loan increases. So we want to now ask the counterfactual question, conditioned on an individual having low net worth and the fact their loan was just kind of denied, what would we expect had we increased their net worth in this context? Feels like their loan probability should increase. But what we found when we trained a causal model without any additional constraints is that that wasn't the case. Actually, in this context, when you condition on that information, increasing their net worth reduced the likelihood that they would get a loan. Which seems really counterintuitive and actually wrong in this context, right? Because it's completely not what we would expect given our knowledge of the financial industry and so forth. So the model here actually decreases probability. So this is showing us that unless we impose additional constraints, there are some counterfactuals that are just kind of wrong given the domain knowledge we might have access to. So the kind of main issue here was that the ordering between the interventions, if I increased net worth, it was always the case that the likelihood of loan approval went up. in this case, those interventions, that ordering was flipped in the counterfactual context. And so we might want to ask, what happens if we just enforce that the ordering on interventions is the exact same as the ordering in the counterfactual context? And so we did that. We imposed this kind of definition here. It's kind of just ensuring that the ordering we see when we look at interventions is reproduced in the counterfactual context. And what we showed was that there's an easy way to say, OK, if this is true, you can now find an easy way to enforce your model to learn these types of counterfactuals. So you just ensure that they're monotonic, which is that when you increase the input, all else being equal, the output at least doesn't decrease. So when you enforce this on the functions underlying your causal model, you get kind of nice, interpretable, and trustworthy counterfactuals. So in the binary case, this actually uniquely identifies all counterfactuals, which is great. Beyond that, in a kind of the categorical case, we can kind of impose this. It doesn't completely identify the counterfactuals, but it's partially identifies them. And so what we should do is we should say, in this case, we should trust the counterfactuals that the model outputs, because the strange, non-intuitive ones have been thrown out. So what we should also note is that the causal analyst looking at the data should be the one to decide if a certain assumption is reasonable given the domain. So we're not saying this should be true for all causal models, but in lots of contexts, like the kind of financial industry and also epidemiology, this seems intuitive. So you can then go on and figure out how to train causal models given this extra constraint. So when you do that, you find that actually you get the correct intuitive probabilities. Given we observe someone had low net worth and they were denied a loan, we want to ask, in that context, had we increased their net worth, would their likelihood of getting a loan increase? And when we impose these constraints, the answer is yes. So it's great. So it seems trustworthy in this kind of context. We can then go on and kind of figure out how to train a causal model given this extra constraint. So I'll skip over this, but if you're interested, it's in a kind of paper that I'll talk about at the end. And we can now get to the answer to that question that I proposed earlier. Is it the right thing to do to scale this protection of springs across kind of Africa in this context? So I want to ask, given that someone got diarrhea and they drank from a protected spring, would they have not got diarrhea had they not drunk from a protected spring? And that probability is very low, which is actually surprising because it tells us that actually it was something else. It was, children would likely have still had diarrhea even if the springs had been protected, given they drank from an unprotected spring. So it was something else than the protection of the water springs in this manner that has the effect on kind of reducing childhood diarrhea. It could be the educational program that went in and talked about that. And so this analysis can't tell us what that extra thing was, but it kind of suggests to the kind of NGO to kind of look for alternative explanations and perhaps run another control trial and scale that thing up if it has a bigger effect and so forth. So that's the kind of last thing. That's the paper there if you're kind of interested. And the last thing to say is I haven't really talked about Spotify at all here. So what has any of this got to do with Spotify? So I'll give you a kind of brief overview of some of these things. I'll just focus on the kind of last one here. So if any of you have listened to Spotify, you can go onto the homepage and songs are recommended, you listen to them and so forth. So a counterfactual question I might want to ask is, okay, given that somebody listened to a certain type of content, song, podcast, whatever, and they were engaged, they kept listening to that style of thing, I want to ask, in that context, had I shown different content, would they have still been engaged? This could suggest other things I could recommend to them or other things I shouldn't recommend to them because it wouldn't have a good impact. And so doing this actually is a counterfactual question and helps me learn something new about that user. Right? On top of all the data I have about them, I've now inferred that a certain type of content for them was linked with enjoyment. So I update my knowledge about any unobserved things that might be going on, their mood and various other kind of predispositions to certain genres and so forth. And in that context, I can now make more accurate inferences and so forth. So that's kind of my entire talk today. I talked about counterfactuals, why they might be useful. And I'd like to note that there are lots of more applications of Spotify beyond those kind of ones. So we're currently hiring, so people are interested, please come and chat to me. Always interested to talk causal inference as well. So thanks very much for your time, and that's me today.